In the deepest silences of the cosmos there are whispers, faint ancient murmurs carried across unimaginable voids of space and time. For centuries we have built instruments of sublime sensitivity, vast metallic ears turned toward the heavens listening. We trained them to hear the echoes of creation itself. We sought the grand, coherent story of our universe, a narrative we thought we were finally beginning to understand. But on a cold, clear night, under the dome of a remote Chilean observatory, one of those whispers arrived differently. It was not a confirmation, it was a contradiction. A single point of light, catalogued with the unpoetic designation AT25P64, carried a message that has begun to unravel everything we thought we knew. This faint photon stream travelled for over 13 billion years to reach us. Its journey began when the universe was an infant, and what it revealed was not the expected chaos of cosmic dawn. It showed an impossible order, a structure that simply should not exist. The data was checked, rechecked, and checked again. There was no error in the instruments, there was no mistake in the calculations. The only error, it seems, was in our fundamental comprehension of reality. The story of the cosmos, our story, is about to be rewritten. What we found at a T25P64 is the beginning of a revolution. It is the evidence that shatters our cosmology. To grasp the magnitude of this fracture, we must first appreciate the edifice it threatens. Our current model of the universe is one of the greatest intellectual achievements in human history. A towering structure of theory and observation, built stone by stone over millennia. It began with our earliest ancestors gazing at the celestial ballet. They saw a comprehensible, predictable, and divine theatre wheeling above them. The Babylonians meticulously charted the heavens to predict omens. The ancient Greeks sought to impose a mathematical perfection upon the sky. They envisioned a cosmos of crystalline spheres, with a stationary Earth at its core. This geocentric vision, elegant and philosophically satisfying, held sway for nearly 2,000 years. It was a model born of human intuition, placing us at the very centre of importance. That comfortable certainty was first dismantled by a series of courageous minds. Nicholas Copernicus, a Polish canon, dared to propose a sun-centred system. He displaced humanity from its privileged position, a demotion that resonated with profound discomfort. Johannes Kepler, through painstaking analysis of planetary orbits, discovered they were not perfect circles. The paths were ellipses, a subtle but critical departure from divine perfection. Galileo Galilei then turned a new invention, the telescope, toward the heavens. He unveiled a universe far richer and more complex than anyone had imagined. Moons orbiting Jupiter proved that not everything revolved around the Earth. The phases of Venus demonstrated its orbit around the Sun. The mountains and valleys on our own moon showed it was a world, not a flawless celestial orb. Each discovery was a chisel blow against the ancient Earth-centric worldview. The intellectual landscape was finally cleared for the towering intellect of Isaac Newton. He provided the universal law that governed it all: gravity. The same force that pulls an apple to the ground keeps the moon in its orbit. The same principles govern the celestial and the terrestrial. Newton's universe was a magnificent, infinite and eternal clockwork mechanism. Set in motion by a divine watchmaker, it operated on immutable laws. It was a static cosmos, existing without a beginning and without an end. For centuries, this Newtonian conception of an unchanging infinite stage seemed unassailable. It was a universe of absolute space and absolute time. A rigid, predictable backdrop against which the drama of existence unfolded. But at the dawn of the 20th century, a young patent clerk in Bern, Switzerland, began to ponder the nature of light and motion. Albert Einstein, through a series of profound thought experiments, would demolish Newton's stage. He revealed that space and time were not absolute. They were relative, malleable, interwoven into a single continuum, space-time. His theory of general relativity, published in 1915, was a complete reimagining of gravity. Gravity was not a mysterious force acting at a distance. It was the curvature of space-time itself, caused by the presence of mass and energy. Imagine space-time as a vast, stretched rubber sheet. A heavy bowling ball representing a star like our Sun, placed in the centre, creates a deep depression. A smaller marble, representing a planet rolling nearby, will not be pulled by a force. Instead, it follows the curve in the sheet created by the bowling ball. It's compelled by the geometry of its environment to orbit the larger mass. This was a staggering conceptual leap. The universe was not a passive stage, it was an active participant in its own evolution. Einstein's equations described a dynamic, restless cosmos. In fact, his own calculations initially suggested the universe must be either expanding or contracting. This idea was so radical, so contrary to the prevailing scientific consensus of a static cosmos, that Einstein himself recoiled from it. He introduced a fudge factor, the cosmological constant, to force his equations to yield a stable universe. It was a decision he would later call his greatest blunder. The observational proof of Einstein's dynamic reality would come from a former lawyer and amateur astronomer. Edwin Hubble, using the colossal new 100-inch Hooker telescope at Mount Wilson Observatory, made two discoveries that would forever alter our cosmic address. First, in 1924, he proved that the so-called spiral nebulae were not clouds of gas within our own Milky Way. They were unimaginably distant, standalone island universes, galaxies just like our own, each containing billions of stars. The known universe expanded in an instant from one galaxy to hundreds of billions. Our home was not the entirety of existence, but a single grain of sand on an infinite cosmic shore. Hubble's second discovery was even more profound. While studying these distant galaxies, he noticed a peculiar phenomenon in their light. The light was stretched, its wavelength shifted toward the red end of the spectrum. This red shift was a cosmic Doppler effect. Just as the pitch of a siren deepens as it moves away from you, the light from a receding object becomes redder. Hubble found that virtually every galaxy was moving away from us, and more astonishingly, the farther away a galaxy was, the faster it was receding. The conclusion was inescapable. The universe was expanding, all of it, everywhere, at once. This was not an explosion of galaxies through a pre-existing empty space. It was the very fabric of space-time itself stretching, carrying the galaxies along with it. A helpful analogy is to imagine a loaf of raisin bread dough rising in an oven. As the dough expands, every raisin moves away from every other raisin. From the perspective of any single raisin, all the others appear to be rushing away. The raisins farther away will appear to move faster because there is more expanding dough between them. We're on one of those raisins, and what Hubble saw was the cosmic dough expanding in all directions. Einstein's blunder was no blunder at all. The universe was alive, dynamic, and growing. If the universe is expanding today, then in the past it must have been smaller. And if you rewind the cosmic clock far enough, everything must have been compressed into a single point, a state of unimaginable density and temperature. This was the logical beginning implied by Hubble's observations. The theory was championed, and even named by a Belgian priest and physicist named Georges Lemaitre. He called it the hypothesis of the primeval atom, a day without a yesterday. His idea, later derisively nicknamed the Big Bang by its detractors, was the ultimate origin story. It proposed that our entire universe, all space, time, matter and energy, erupted from a singular point some 13.8 billion years ago. For decades, this theory remained a compelling but unproven hypothesis. Then, in 1964, the first great pillar of evidence was discovered entirely by accident. Two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were trying to eliminate a persistent, annoying hiss from their horn-shaped radio antenna. The noise was uniform, coming from every direction in the sky, day and night, through every season. They cleaned their equipment, even removing pigeon droppings, but the faint hum remained. They had stumbled upon the oldest light in the universe, the afterglow of creation, the cosmic microwave background radiation. This faint energy is the remnant heat from the primordial fireball. For the first 380,000 years, the universe was a superheated, opaque plasma, a searing fog of protons, neutrons and electrons where light could not travel freely. But as the universe expanded, it cooled. Eventually it reached a critical temperature where electrons could combine with nuclei to form the first atoms. the cosmos suddenly became transparent. The light that was present at that moment was finally set free, and it has been travelling through the universe ever since. As space has stretched over billions of years, the wavelength of this primordial light has also stretched. From brilliant visible light, it has been redshifted all the way down to the microwave part of the spectrum. Penzias and Wilson had found the faint residual warmth of the Big Bang itself. It was a stunning confirmation, earning them the Nobel Prize. A second pillar of support came from the chemistry of the cosmos. The Big Bang model makes extraordinarily precise predictions about the composition of the early universe. In the first few minutes after the initial expansion, conditions were perfect for nuclear fusion. Protons and neutrons fused to form the nuclei of the lightest elements. The theory predicted a universe composed of roughly 75% hydrogen, 25% helium, and trace amounts of lithium. When astronomers point their telescopes to the most ancient, pristine gas clouds in the distant cosmos, this is precisely the chemical mixture they find. The consistency between theoretical prediction and astronomical observation is a triumph of the model. The third pillar is the large-scale structure of the universe we see today. Detailed maps of the cosmic microwave background from missions like COBE, Dulles-Map and Planck reveal that the early universe was not perfectly uniform. It contained minuscule temperature fluctuations, tiny variations in density from one spot to another. These ripples were the seeds of all future structure. Imagine a nearly flat, calm ocean with incredibly subtle waves on its surface. Over billions of years, the relentless force of gravity acted on these slight variations. Regions that were infinitesimally denser began to pull in more matter. The rich got richer. Slowly, painstakingly, gravity sculpted the cosmic web. Vast filaments of gas and galaxies separated by immense dark voids. Our modern universe, with its clusters, galaxies, stars and planets, grew directly from those primordial seeds. This grand narrative, known as the lambda-cold dark matter model, became our standard cosmology. It was a story of cosmic evolution from a hot, dense beginning to the magnificent structured cosmos of today. It explained so much, so elegantly, that it became the bedrock of modern physics. But even the most solid bedrock can hide deep, unsettling faults. Our standard model, for all its successes, rested on two profoundly mysterious entities. The first was discovered through the motion of the stars themselves. In the 1970s, astronomer Vera Rubin was studying the rotation of spiral galaxies. She expected to find that stars farther from the galactic centre would orbit more slowly, just as outer planets in our solar system move slower than inner ones. Newton's laws of gravity were clear on this point, but what she observed was astonishing. The outer stars were moving just as fast as the inner ones. The galaxies were spinning far too rapidly. Based on the visible matter, the stars, gas and dust, they should have flown apart. Think of a spinning merry-go-round. If you spin it too fast, the children on the edge will be flung off. Vera Rubin saw galaxies spinning at this reckless speed, yet they remained intact. There had to be some unseen substance, a tremendous amount of invisible mass, providing the extra gravitational glue needed to hold everything together. This mysterious substance was dubbed dark matter. It does not emit light, it does not absorb light, it does not reflect light. It interacts with our world only through the subtle, persistent pull of its gravity. Scientists have built incredibly sensitive detectors deep underground to try and catch a fleeting dark matter particle. So far, they have all remained silent. Yet according to our models, this invisible material outweighs all the normal matter in the universe by a factor of 5. We live in a cosmos dominated by a substance we cannot see and do not understand. This was the first great mystery embedded within our standard model. The second mystery arrived with an even greater shock. In the late 1990s, 2 independent teams of astronomers set out to measure the expansion rate of the universe. They were using Type 1a supernovae, exploding white dwarf stars, as standard candles. These explosions have a known, uniform brightness, allowing astronomers to calculate their distance with great precision. The teams expected to find that the universe's expansion was slowing down, pulled back by the collective gravity of all the matter within it. What they found was the exact opposite. The expansion of the universe is not slowing down, it is accelerating. This was a discovery that shook cosmology to its core. It was like throwing a set of keys into the air and watching them shoot upward, faster and faster, instead of falling back down. Some unknown energy, some repulsive force inherent in the fabric of space itself, is overwhelming gravity on cosmic scales and pushing the universe apart at an ever-increasing rate. This mysterious influence was named dark energy. It is even more enigmatic and more dominant than dark matter. According to our best measurements, this dark energy accounts for nearly 70% of the total energy density of the cosmos. Our standard model, the lambda-CDM model, is named for it. Lambda, Einstein's cosmological constant, resurrected to represent this dark energy, and cold dark matter, the invisible scaffolding on which galaxies are built. So our grand understanding of the cosmos is this: about 5% is the normal luminous matter that makes up everything we have ever seen. 27% is an invisible form of matter we have never directly detected, and 68% is a mysterious, repulsive energy we cannot explain. We have constructed a detailed map of the universe while being fundamentally ignorant of 95% of its contents. Even within this framework of profound ignorance, troubling inconsistencies began to emerge. Chief among them is a growing crisis known as the Hubble Tension. The Hubble constant is a measure of how fast the universe is expanding today. There are two primary and highly precise ways of measuring this value. One method looks at the very early universe. By studying the fluctuations in the cosmic microwave background, the echo of the Big Bang, scientists can use the standard model to predict what the expansion rate should be today. It's like analysing the initial burst of a firework to predict how its embers will be distributed moments later. This method gives a value of about 67 km per second per megaparsec. The second method looks at the local, modern universe. It uses standard candles like supernovae and pulsating Cepheid variable stars in nearby galaxies to directly measure the current rate of expansion. This technique is akin to using a radar gun to clock the speed of passing cars. This direct measurement consistently yields a higher value, around 73 km per second per megaparsec. The difference might seem small, but the error bars on these measurements no longer overlap. The universe appears to be expanding faster than our model, based on the early universe predicts it should. It suggests there is a missing ingredient in our cosmic recipe, a fundamental flaw in our understanding of the universe's evolution from its infancy to its current state. The tension was tightening. The cracks in the foundation of cosmology were beginning to show. And it was into this landscape of simmering uncertainty that the light from a T25P64 finally arrived. The designation AT25P64 refers not to a star nor a conventional galaxy. It is an object known as a quasar, an intensely luminous galactic core powered by a supermassive black hole. This particular quasar is one of the most distant ever observed. Its light began its journey to Earth when the universe was less than 5% of its current age, a mere 600 million years after the Big Bang. It is a time capsule from the cosmic dawn. The James Webb Space Telescope was tasked with observing this object, not to study the quasar itself, but to study what lies in front of it. As the quasar's light travelled across the cosmos, it passed through the halo of a foreground galaxy, a primordial galaxy that existed even earlier in cosmic history. The gases in this ancient galaxy absorbed some of the quasar's light, leaving a faint, ghostly fingerprint in the spectrum. A barcode of absorption lines that astronomers could read. What the team of astrophysicists expected to see was the chemical signature of a proto-galaxy. A small, messy, chaotic collection of primordial hydrogen and helium gas. A galactic embryo, just beginning the slow, billion-year process of gravitational collapse. This is what our standard model of cosmology, with its cold, dark matter scaffolding, predicts. Small things form first, and then merge over eons to create larger structures. The universe should be bottom up. The first galaxies ought to be small, irregular, and chemically simple. Massive, well-ordered spiral galaxies like our own Milky Way should take billions of years to assemble. The data from a T25P64 came back from the telescope, and it was impossible. The spectral fingerprint was not that of a primordial gas cloud. The absorption lines showed the distinct chemical signatures of heavier elements: carbon, oxygen, silicon. These are elements forged only in the hearts of massive stars, then scattered into space when those stars die. To see them in such abundance meant this galaxy had already lived through multiple generations of star birth and death. It was not a galactic embryo, it was a fully mature, chemically enriched galaxy. Further analysis of the spectral lines revealed something even more shocking. The gas was not in a chaotic, turbulent clump. It was moving in a well-ordered, rotating disk. The signature was unmistakable: a large, stable, rapidly spinning spiral galaxy. A structure that, according to our bedrock cosmological model, should not and could not exist so soon after the beginning of time. It was the cosmic equivalent of finding a fully grown oak tree just 1 week after planting an acorn. It defies the known laws of growth and development. This single object, a ghost galaxy imprinted on the light of a background quasar, presents a direct, falsifying observation of our most cherished cosmological theory. The first reaction in the scientific community was profound disbelief. Every possible source of error was investigated. Could the quasar's light have been gravitationally lensed, creating a distorted image? The calculations showed no such effect. Could the foreground object be a much closer, smaller galaxy, masquerading as an ancient one? The redshift was unambiguous, placing it firmly in the early universe. The data was reanalyzed by competing teams, all hoping to find the flaw. But the conclusion was robust. The impossible galaxy was real. It existed. This shatters the assumption of a slow bottom-up formation of structure. If massive, mature galaxies can form this quickly, then the cold in cold dark matter might be wrong. Perhaps dark matter is warmer, or interacts with itself in ways we haven't imagined, allowing it to clump together much more rapidly in the early universe. Or perhaps the initial seeds of structure, the tiny fluctuations in the cosmic microwave background, were not as subtle as we believed. Maybe there were larger primordial density variations that could jumpstart galaxy formation. This would require rewriting the physics of cosmic inflation, the theory that describes the universe's first moments. The implications ripple outward, touching every aspect of our cosmic story. The existence of such an object so early could even help explain the Hubble tension. If the universe formed structure faster and differently than our model assumes, then our calculation of the Hubble constant from the early universe is based on a false premise. The conflict between the early and late universe measurements might not be a conflict at all. It might be the sound of our old model breaking apart under the weight of new evidence. A T25 P64 is not just another puzzling data point, it is a paradigm killer. It tells us that our grand narrative, for all its beauty and predictive power, is incomplete. Perhaps it is fundamentally wrong. We find ourselves at a precipice, staring into a vast intellectual chasm. The old map is now unreliable, and the new one has yet to be drawn. This is a terrifying, but also exhilarating moment in the history of science. It forces us to ask bolder, more imaginative questions. What if the problem isn't with dark matter, but with gravity itself? For decades, a minority of physicists has explored theories of modified gravity. These models suggest that on galactic and cosmic scales, gravity does not behave as Einstein predicted. Perhaps there is no dark matter. Perhaps the accelerated rotation of galaxies is a sign that our law of gravity is incomplete. These theories have long been considered fringe ideas, but observations like AT25 P64 are forcing them into the mainstream. Or could the truth be even more radical? The Big Bang model assumes a singular beginning from nothing. But what if it was not a beginning, but a transition? Cyclic universe models propose a cosmos that undergoes an endless series of expansions and contractions, a big bounce rather than a big bang. In such a scenario, the structure we see could be an inheritance. The seeds for massive galaxies like the one revealed by AT25 P64 might have been forged in a cosmic era that predated our own. We might be living in one chapter of an eternal cyclical book. This idea stretches our conception of time and existence into infinity. This single observation pushes us toward the very edges of theoretical physics. Ideas born from string theory and M theory, which postulate extra dimensions of space, may offer new mechanisms for the behaviour of the early universe. Perhaps what we're seeing is evidence of phenomena from another dimension, its influence leaking into our own. It forces us to confront the unsettling possibility that the laws of physics themselves may not be constant, that they can vary in different epochs of the universe's history, or even in different locations. We have been navigating the cosmos with a single set of rules. A T25P64 suggests there might be a more complex and far more wondrous game in play. The comfortable, comprehensible cosmos of our standard model is dissolving. In its place is a deeper mystery, a more profound unknown. This is not a failure of science. It is the very essence of the scientific process. It is the willingness to abandon our most cherished beliefs in the face of contrary evidence. We stand today in a position similar to the astronomers just before Copernicus and Galileo. We have been observing epicycles, adding complexities to a model that is groaning under its own weight. Dark matter and dark energy might be the modern equivalents of those celestial spheres, elaborate constructs designed to save a theory that is no longer tenable. A T25P64 is the telescope pointed at Jupiter's moons, revealing a truth that cannot be unseen. We are adrift once more, our cosmic map torn to pieces. But from this disarray, a new, more accurate understanding will eventually emerge. The next generation of telescopes, theorists, and thinkers will build a new cosmology from these ruins, one that incorporates this impossible, ancient galaxy and all the other anomalies we have tried to ignore. The search for this new model will be the great scientific adventure of the 21st century. It will require leaps of imagination as profound as those of Newton and Einstein. The universe, it seems, is not just stranger than we imagine. It is stranger than we can imagine. The light from a 25P64 travelled for more than 13 billion years to deliver its disruptive message. It reminds us that our quest for knowledge is never complete, that with every circle of light our instruments draw from the darkness, the circumference of our ignorance also expands, and that hidden in the deepest, oldest corners of the night sky are secrets that are waiting to shatter our assumptions and to show us a cosmos more magnificent and more mysterious than we ever dared to dream. The age of comfortable cosmology is over. A new era of discovery has just begun. What does it mean to be alone? As a species, we have grappled with this question since the moment we first recognized the stars, not as celestial decorations, but as other suns, other possibilities. We have spent centuries gazing into the cosmic ocean, turning our most advanced instruments toward the silent darkness, listening for a whisper, a signal, a faint structured murmur against the chaotic symphony of the universe. We've built colossal ears of steel and wire dishes aimed at the heavens, straining to catch a single intelligent note that would tell us we are not the only thinking beings in this incomprehensibly vast expanse. We have shouted our own messages into the void, encoding our science, our music, our very humanity onto golden records and beaming them toward distant stellar shores. They are our messages in a bottle cast upon an abyss of space-time so profound that we cannot even be certain if there is another shore to wash up on. For all our searching, for all our listening, for all our hope, the cosmos has met our query with a profound, almost deafening silence. The Fermi paradox, a simple yet terrifying question, hangs over all of our astronomy. If the universe is teeming with life, where is everybody? The silence itself has become a kind of data, a piece of evidence that suggests a range of possibilities, from the chillingly lonely to the profoundly strange. Perhaps life is impossibly rare, a chemical miracle confined to this one pale blue dot. Perhaps civilizations inevitably destroy themselves before they can master the stars. Or perhaps, just perhaps, they are out there, but they communicate and travel in ways we are too primitive to even recognize. We have been searching for a language we might understand, a signal broadcast on a familiar wavelength. We have been looking for neighbors. We never truly prepared for the possibility that the first contact would not be a message but a visitor, an object, a silent passerby from a place we can only dream of. To understand the magnitude of what happened in 2017, you must first appreciate the gulf it crossed. The space between stars is not merely empty, it is the most perfect and hostile vacuum ever conceived. It is a realm of such crushing emptiness that a single atom every few cubic centimeters is considered dense. Here the temperature plunges to a few degrees above absolute zero, the theoretical point where all atomic motion ceases. This is a cold so deep it can shatter the bonds of molecules, a stillness that preserves everything and yet permits nothing to live in the way we understand it. Through this eternal twilight drift the cosmic rays, the shrapnel of supernova explosions, and the fury of black holes. They are the universe's stray bullets, atomic nuclei stripped bare and accelerated to nearly the speed of light. They tear through matter, shredding DNA, corrupting electronics, and slowly, inexorably eroding the very fabric of any object that dares to cross the interstellar void. A journey of 1,000,000 years through this shooting gallery is not just a trip, it is a war of attrition against physics itself. Anything making such a voyage must be incredibly resilient, ancient, and patient. For millennia, our solar system has been an isolated island, a self-contained whirlpool of planets, asteroids, and comets, all born from the same spinning cloud of gas and dust, all gravitationally shackled to our parent star. We knew theoretically that other islands must exist. We knew that just as our sun occasionally flings a comet out into the interstellar darkness, other suns must do the same. Astronomers predicted that eventually a piece of another solar system would drift through our own. They even had a profile for what it would look like. It would be a comet, a dirty snowball ejected from its home star's orbit millions or even billions of years ago. As it neared our sun, the warmth would sublimate its icy surface, creating a magnificent ghostly tail, a visible, predictable signature of its origins. We built new telescopes, powerful digital eyes like the Panoramic Survey Telescope and Rapid Response System, or PAN-STARRS, perched atop the Haleakala volcano in Hawaii. Their nightly vigil was designed to scan the entire visible sky, looking for the faint smudges and streaks of light that betray the movement of asteroids and comets, particularly those that might pose a threat to Earth. We were standing watch guarding our shores, but we were also waiting. We were waiting for that first long-expected traveller. We thought we were ready. We thought we knew what to expect. We couldn't have been more wrong. On the 19th of October 2017, a discovery was made. It wasn't a flash of insight or a sudden eureka moment. It was a single, unremarkable point of light flagged by a computer algorithm. An object designated A, 2017U, one was moving fast, very fast. At first, astronomers assumed it was a small nearby asteroid, its high apparent speed a simple trick of perspective. But as observatories around the world turned their gaze to this fleeting visitor and tracked its path, a shocking and unprecedented reality began to dawn. They calculated its orbit, running the numbers again and again, certain there must be an error. There was no error. The object's trajectory was not a closed ellipse, the familiar repeating path of every planet, asteroid, and comet bound to our sun. Its path was an open-ended hyperbolic curve. It had screamed into our solar system from above the ecliptic plane, the flat disk where the planets reside, at a velocity so extreme that the sun's gravity could only bend its path, not capture it. It was not from here. It was not one of ours. It was a true interstellar object, the first ever confirmed by humanity. The news rippled through the astronomical community with the force of a tidal wave. This was it, the moment we had been waiting for. A piece of another star system delivered to our doorstep. It was quickly given a new, more fitting name by its discoverers in Hawaii, Oumuamua. In the Hawaiian language, it means a messenger from afar arriving first. The name was poetic, perfect. It captured the profound significance of the encounter. For the first time, we had a tangible link to another star, a physical sample we could study. But the clock was ticking, and Oumuamua was already on its way out. It had made its closest pass to the sun weeks before it was even spotted, and it was now hurtling away from us at over 100,000 miles per hour, its faint light fading with every passing moment. Astronomers had a desperately narrow window to learn everything they could. They threw every available telescope at it, from the Hubble Space Telescope to the Very Large Telescope in Chile, racing against its departure. And as the first precious photons of data streamed in, the initial excitement began to mix with a profound and deepening sense of confusion. The messenger, it seemed, was not what we expected at all. The very first clue that Oumuamua was deeply strange was what it lacked. Our models, our predictions, our every expectation had prepared us for a comet. As this icy body from the cold depths of interstellar space approached our warm sun, it should have outgassed. The solar radiation should have vaporized its surface, shrouding it in a beautiful glowing coma, a halo of gas and dust. This coma is what gives comets their iconic tails and makes them brightly visible. But as our most powerful telescopes stared at Oumuamua, they saw nothing. Nothing but a single sharp point of starlight. There was no fuzziness, no gas, no dust, not even a trace. It was utterly inexplicably clean. If it was a comet, it was unlike any comet we had ever witnessed. Perhaps then it was an asteroid, a dry, sterile rock baked clean of any ices by a long and arduous journey. This seemed plausible, a simple solution to the missing coma. Yet this explanation created a new set of problems. Asteroids are typically reddish in colour, a hue they acquire from eons of bombardment by cosmic rays that alters their surface chemistry. And Oumuamua was indeed reddish, a dark, rich, organic red consistent with a body that had travelled for an unimaginable length of time. But there was another, far more bizarre characteristic that a simple rock could not explain. As it tumbled through space, its brightness changed, swinging wildly by a factor of 10 every 7 to 8 hours. Think about that. An object was becoming 10 times brighter, then 10 times dimmer in a regular repeating cycle. There is only one way for that to happen. The object could not be spherical like a ball or even lumpy like a typical potato-shaped asteroid. To produce such an extreme variation in reflected light, it had to have a truly radical shape. The data suggested it was at least 10 times longer than it was wide. The mathematical models painted a picture of something utterly alien to our solar system. A cosmic needle, a celestial cigar. Or perhaps something else entirely, something very long, very wide, but extraordinarily thin, like a shard or a pancake tumbling end over end. Whatever its precise form, it was a shape that defied easy natural explanation. How could the random processes of celestial mechanics sculpt such a bizarrely elongated sliver of rock and then send it on a journey between the stars? The mystery was growing deeper with every observation. Oumuamua was not behaving. It refused to fit into any of our neat pre-packaged categories. It was a messenger, yes, but its message was becoming increasingly cryptic, and its biggest surprise was yet to come. As astronomers continued to track Oumuamua's frantic escape from our solar system, they noticed something that at first seemed impossible. It was accelerating. The deviation was minuscule, a tiny, almost imperceptible nudge, but it was statistically undeniable. The object was moving away from the sun slightly faster than gravity alone could account for. It was being pushed by an unseen force. For a normal comet, this is perfectly normal behavior. As the sun heats, the comet's surface jets of gas and dust erupt like thrusters on a spacecraft, giving it a gentle, non-gravitational push. This is the very reason we expected Oumuamua to have a coma in the first place. The acceleration was the smoking gun for outgassing. But this created an immediate and profound contradiction. How could Oumuamua be accelerating due to outgassing when our most powerful telescopes could see absolutely no gas? The limits were incredibly stringent. If there were jets, they had to be made of a material so perfectly transparent and fine that it was invisible to our entire suite of instruments, yet strong enough to measurably alter the trajectory of a quarter-mile long object. No known substance behaves this way. The push was also remarkably smooth. Cometary jets are typically clunky and uneven, causing the object to spin and wobble unpredictably. Oumuamua's acceleration was a steady, graceful push consistent across the entire arc of its departure. The pieces of the puzzle were not just failing to fit, they seemed to come from entirely different boxes. It had the dark reddish colour of a long-journey asteroid, but a shape that was wildly improbable. It had the non-gravitational acceleration of a comet, but a complete and baffling absence of any cometary activity. It was a rock that behaved like a comet that looked like a rock, It was a paradox, a cosmic riddle wrapped in an enigma, and it was disappearing into the void forever. In the face of these contradictions, science did what it does best. It tried to find a natural explanation, no matter how exotic. Perhaps it was a new type of object we'd never considered, like a nitrogen iceberg chipped off a Pluto-like planet in another star system. Such an object might outgas pure invisible nitrogen, but this would require a source object of a type we have yet to prove exists. Perhaps it was a cosmic dust bunny, a fractal aggregate of material so light and porous that the gentle pressure of sunlight alone could push it. But it is difficult to imagine how such a fragile structure could survive a journey of millions of years through the interstellar medium. Every natural explanation grew more convoluted, more complex, requiring special circumstances and invoking objects we had never seen. And as each conventional theory was examined and found wanting, a door began to creak open to a far more audacious, a far more unsettling possibility, one that took the observed facts at face value. What if the bizarre shape wasn't an accident? What if the strange, gentle acceleration wasn't from some invisible gas? What if the push came from the sunlight itself, acting on a surface area to mass ratio so extreme that it behaved, less like a rock and more like a sail? What if, after all our years of listening for a message, the first sign of extraterrestrial intelligence wasn't a radio wave, but a piece of technology? This was the electrifying hypothesis put forward by astronomers at Harvard University. They argued that Oumuamua could be a light sail, a craft designed to be propelled by the pressure of starlight. Its extreme thinness, its lack of outgassing, and its gentle solar-powered acceleration all clicked into place if one dared to consider an artificial origin. It was an idea that sent shockwaves through the scientific world, a proposal many considered a leap too far, a betrayal of the principle that one should not invoke extraordinary claims without extraordinary evidence. The debate ignited instantly, a fierce and passionate firestorm that continues to this day. Was this brilliant Occam's razor the simplest explanation that fit all the data, or was it an argument from ignorance? A fanciful leap into science fiction simply because our understanding of cosmic nature was incomplete. But this documentary will explore an even more profound, more challenging extension of that idea. It is a hypothesis that pushes the boundaries not only of astronomy, but of biology and our definition of life itself. What if Oumuamua was not just a machine? The raw, unfiltered violence of interstellar travel, the endless bombardment by cosmic rays, the eons of deep cold poses, an almost insurmountable challenge for conventional technology as we know. But nature through evolution has already solved the problem of resilience. What if a civilization eons beyond our own merged technology with biology? What if they engineered not a dead probe of metal and silicon, but something more akin to a seed, a spore, or a vessel with a self-healing, radiation-resistant, biological hull, a craft designed not just to endure the journey between the stars, but to thrive in it, a biological artifact? Is it possible that the messenger from afar was not just carrying a message, but was in some fundamental way alive? This is the story we will now investigate. We will peel back the layers of data, we will listen to the brilliant minds on both sides of this historic debate, and we will venture to the very edge of what we know about life and technology. We will chase this ghost through the cosmos, for in its fleeting passage, Oumuamua may have given us more than just a scientific puzzle. It may have given us our first tantalizing glimpse of our own future, and our first real evidence that we are not, after all, alone. For millennia, we have strained our ears listening to the profound and seemingly empty silence of the cosmos. We have built colossal dishes to catch the faintest whispers from distant stars scanning the heavens for a signal, a pattern, a single deliberate note in the grand chaotic symphony of the universe. We searched for a message sent to us. We never imagined the first one would be delivered in person, a silent courier from an unknown shore hurtling through our planetary home without so much as a greeting. It arrived not with a bang but as a ghost, a fleeting, anomalous flicker of light against the infinite black. This is the story of that first visitor, the emissary we almost missed, and the chilling questions it brought with it. A story that began on an ordinary night when one of our tireless sentinels perched atop a dormant volcano saw something that should not exist. High on the summit of Haleakala, on the Hawaiian island of Maui, sits an extraordinary eye. It is not organic, but it is relentlessly vigilant. This is the Panoramic Survey Telescope and Rapid Response System, or PAN-STARRS. Its mission is not to gaze in awe at beautiful faraway nebulae, but to perform a far more urgent task to guard our world. Night after night, its 1.8-meter mirror scans the celestial sphere, taking thousands of images, building the most detailed map of the moving sky ever conceived. Its powerful computers sift through a deluge of data, a torrent of light, searching for the faintest motion. They are programmed to find the near-Earth asteroids and comets, the celestial debris from our own solar system's formation that could one day pose a threat to our existence. It is a tireless automated watchman charting the familiar orbits of our cosmic neighbours. But on October 19, 2017, this sentinel flagged an object so bizarre, so utterly alien, that it broke every rule in the astronomical playbook. At first, it was designated A, 2017U1, a dry, unassuming label for what was to the software just another fast-moving rock. The initial alert rippled through the global astronomical community, a routine notification that quickly began to gather an anxious energy. Astronomers around the world swiveled their own telescopes toward this faint speck, trying to plot its course to understand its provenance. And as the data points accumulated, a picture began to form, a picture that was deeply and fundamentally wrong. Everything we thought we knew about the architecture of our solar system is built upon the elegant, predictable laws of gravity. Objects orbit our sun in closed loops, ellipses, some nearly circular like Earth's, others stretched and eccentric like those of long-period comets. They are all members of our solar family, gravitationally tethered to our star, destined to swing around it for eternity. They are prisoners of the sun's immense gravity. But this object, this was no prisoner. As scientists refined its trajectory, a startling truth emerged. Its path was not an ellipse, it was a hyperbola, an open-ended, unbound arc. This was not a gentle curve bringing an object back for another pass. This was the laser-straight track of an interstellar bullet fired from an unknown point in the cosmos, piercing the plane of our solar system for one brief, violent encounter. It was moving at a blistering 196,000 miles per hour, a speed so immense that the sun's gravity was little more than a temporary inconvenience. Imagine throwing a ball into the air. Gravity ensures it will fall back to you. Now imagine a cannonball fired from miles away that screams past your head and continues on its momentum so great that your entire planet's gravity is powerless to capture it. That was A, 2017 U1. It wasn't just visiting, it was passing through. For the first time in human history, we had incontrovertible proof that we were seeing an object that was not from here. It was a genuine artifact from another star system. The realization was electric. The scientific community renamed it one I, Oumuamua, a beautiful Hawaiian name meaning a messenger from afar arriving first. The name was poetic, but the messenger was deeply troubling. The first great puzzle was its identity. In our solar system, celestial travelers are typically sorted into two main categories, asteroids and comets. Asteroids are the rocky, metallic remnants of planetary formation, inert chunks of stone and iron, mostly confined to the belt between Mars and Jupiter. Comets are the dirty snowballs of the outer solar system, primordial relics of ice and dust from the frigid depths of the Oort cloud. When a comet approaches the sun, its ices vaporize, creating a brilliant glowing halo called a coma, and often a spectacular tail that can stretch for millions of miles. This outgassing, this venting of vapor, acts like a tiny rocket engine, giving the comet a gentle, non-gravitational push that subtly alters its course. This is a well-understood phenomenon. When Oumuamua was discovered, its trajectory plunging in from high above the plane of the solar system screamed comet. This was the expected profile for a long-period comet knocked from its distant orbit. Astronomers around the world trained their most powerful spectrographs on it, searching for the telltale signs of that gaseous coma. They found nothing. Absolutely nothing. There was no dust. There was no gas. There was no water vapor, no carbon monoxide, no trace of the outgassing that should have been happening as this object made its closest approach to our sun just a month earlier. It had swung by our star at a searing proximity closer than the orbit of Mercury, where it should have been baked by a celestial blowtorch. Any ice should have been erupting into space, shrouding the object in a brilliant cloud. But Oumuamua remained stubbornly, inexplicably inert. It was dark, it was dense, and it was completely utterly dry. So if it wasn't a comet, it must be an asteroid, correct? This seemed the only logical alternative. An interstellar asteroid, a piece of another planet from another star flung out into the void by some ancient gravitational cataclysm. It was a breathtaking possibility, a chance to hold metaphorically a piece of an alien world. Yet this explanation too began to fray at the edges. While it looked like an asteroid, it wasn't moving quite like one. There were subtle deviations in its path that gravity alone could not account for, a ghostly acceleration that would become the central, maddening enigma of this object. But even before that mystery took center stage, Oumuamua was preparing to reveal an even more shocking secret. As this cosmic fugitive raced away from us forever beyond our reach, astronomers were in a desperate sprint to learn everything they could. They couldn't see it as a clear image. Even in our most powerful telescopes, it was just a point of light. But they could measure that light with incredible precision, and what they saw was astounding. The light from Oumuamua wasn't steady. It was changing, dimming, and brightening dramatically, pulsing on a regular cycle of about 8 hours. This wasn't a random flicker. It was a rhythmic, predictable variation, and it could mean only one thing. The object was tumbling end over end, and it was not shaped like any asteroid or comet we had ever seen. The brightness variation was extreme, a factor of 10. To produce such a drastic change, the object had to have a truly radical shape. A sphere, a potato shape, even a somewhat flattened disk, would only produce minor fluctuations in reflected light as it spins. To get a 10-fold variation, you need something impossibly extreme. The models delivered a portrait that seemed to be ripped from the pages of science fiction. Oumuamua was a spindle, a sliver, a cosmic needle. It was perhaps 10 times as long as it was wide, maybe 400 meters in length, but only 40 meters across. Imagine a skyscraper laid on its side, tumbling silently through the void. No known natural process in our solar system creates objects with such an extreme aspect ratio. Asteroids are rubble piles clumped together by gravity into lumpy potato-like shapes. Comets are similarly irregular. The forces of accretion and collision tend to average things out, creating objects that are for the most part roughly equidimensional. But this was an anomaly. It was a shard. Its color was a dark, burnished red, the result of untold eons of bombardment by cosmic rays in the interstellar deep, a process that cooks any organic compounds on the surface into a complex carbon-rich crust. It was ancient, weathered, and utterly alone. The revelation of its shape sent a new kind of shockwave through the world of planetary science. The initial excitement of discovering an interstellar visitor was now tinged with a profound sense of unease. What celestial mechanic could forge a rock into the shape of a cigar? What natural process grinds a world down and spits out a needle? The object was defying our neat and tidy classifications. It had the trajectory of a comet, but none of the activity. It had the dry, rocky appearance of an asteroid, but a shape that was wildly unnatural. It was a contradiction wrapped in an enigma, a celestial chimera that seemed almost deliberately designed to confuse us. And it was getting away. The window of observation was terrifyingly brief. Discovered on its way out, it was already receding at a fantastic velocity. Every night it grew fainter. A frantic worldwide campaign began marshalling every available instrument from the Very Large Telescope in Chile to the Hubble Space Telescope in orbit to stare at this fading point of light before it vanished back into the abyss from which it came. The data gathered in those few precious weeks is all we will ever have. Oumuamua will never return. It is already far beyond the orbit of Saturn, a silent ghost receding into the dark. It offered us no explanation for its existence. It simply appeared, presented us with an impossible puzzle, and then departed, leaving behind a trail of profound and unsettling questions. We were left holding a cosmic calling card with no return address. The world's astronomers, who had begun by classifying it as a comet, then reclassified it as an asteroid, were now left with a third unspoken category, the unknown. This was not simply another rock, it was something else. It behaved with a subtle intentionality that was difficult to articulate but impossible to ignore. It was a messenger, but what was its message? Was its bizarre shape a mere cosmic coincidence, a one in a trillion fluke of nature? Was its dry, inert surface a sign of its incredible age, or was it a shield, a hull hardened by its journey? The initial confusion was hardening into a new, more radical line of inquiry. If nature as we know it couldn't produce this object, then perhaps we were looking at the wrong kind of nature altogether. The mystery of its composition and shape was about to be eclipsed by an even greater one, the mystery of its motion. For as scientists plotted its final departing trajectory with painstaking accuracy, they found the ghost in the machine. A whisper of acceleration, a tiny inexplicable push. A push with no visible engine. As it rounded the sun, a fleeting captive of our star's gravity, Oumuamua began its long fall back into the interstellar dark. For the astronomers tracking its departure, this should have been the final predictable act in a brief but thrilling cosmic play. Its trajectory was plotted, the elegant arc of its escape calculated down to the finest decimal, a testament to the clockwork precision of orbital mechanics, a law we thought was written in stone. The sun's immense gravitational grip would act as a perfect sling, flinging our visitor back towards the void on a known path. But something was wrong. Deep within the columns of data streaming back from our telescopes, a subtle rebellion was taking place, a tiny but persistent heresy against the gospel of Newton and Einstein. The object was moving faster than it should have been. The deviation was minuscule at first, a phantom in the numbers easily dismissed as a rounding error or a slight observational jitter. Yet as the days turned into weeks, the anomaly refused to vanish. Instead, it grew, becoming more defined, more certain, more real. Oumuamua was accelerating ever so slightly away from the Sunday. It was being pushed. A gentle, continuous thrust was nudging it along, giving it an extra kick of speed on its outbound journey. This was a violation. The clean, perfect arc of its gravitational path was being contaminated by an unknown force. Imagine throwing a stone into the air and watching it at the very peak of its climb suddenly push itself a little higher before beginning its descent. You would know instantly that you hadn't thrown a simple stone, you had thrown something else entirely. For the scientific community, this non-gravitational acceleration was not in itself a complete shock. We see this all the time. It's the classic signature of a comet. This was the obvious suspect, the first and most logical explanation to be placed on the table, a comforting solution to a budding puzzle. Comets, after all, are not inert rocks. They are active, dynamic worlds. They are cosmic time capsules, dirty snowballs packed with primordial ices, remnants from the birth of our own solar system. As one of these celestial icebergs approaches the fierce heat of a star, its surface begins to boil, but not into a liquid. In the vacuum of space, the ice sublimates, turning directly into gas. These jets of vapor burst from the nucleus like miniature geysers, spewing gas and dust into a vast glowing shroud called a coma. This process is the celestial engine of a comet. The escaping gas acts like a network of tiny, unpredictable thrusters, pushing the nucleus in the opposite direction. This outgassing is the very force that gives comets their famous tails and produces the exact kind of non-gravitational push that astronomers were now observing in Oumuamua. The case, it seemed, was open and shut. Our mysterious interstellar visitor was simply a comet, an emissary from another star's ancient past. And so the great hunt began. Every major observatory that could get a look turned its gaze towards the fading point of light, searching for the telltale signs. The instructions were clear: find the coma, find the tail, find the gas. The Hubble Space Telescope, our sharpest eye in orbit, stared intently, trying to resolve a fuzzy halo of dust and vapor around the object's core. It saw nothing, only a crisp stellar point clinically sharp against the velvet blackness of space. There was no haze, no shroud, no hint of a dusty atmosphere. Perhaps the gas was too thin, comprised only of vapor without the dust. For that, we turned to the Spitzer Space Telescope, a magnificent instrument designed to see the universe not in visible light, but in the invisible realm of heat and infrared radiation. If there were gases like water vapor or carbon monoxide venting from the surface, they would be warmed by the sun, and Spitzer would see their heat signature, an ethereal glow where our own eyes would see only emptiness. Spitzer stared, and for a grueling number of hours it listened for that faint thermal whisper. The silence was absolute. The data came back clean. There was no excess infrared radiation, no trace of water, the most common ingredient in the comets we know, no hint of carbon monoxide or carbon dioxide, the next most likely suspects. Ground-based telescopes scoured the spectrum of light from the object, sifting through its wavelengths for the chemical fingerprints of cyanogen gas, another common cometary component. The result was the same, a resounding, definitive null. This wasn't merely a failure to find evidence. The sheer precision of our instruments turned that lack of evidence into something far more powerful. It was evidence of absence. Oumuamua was pristine. It was inert. It was terrifyingly clean. Yet it was undeniably accelerating. The engine was running, but there was no smoke, no heat, no exhaust. It was a ghost ship sailing on an invisible, impossible wind. The most logical, most comfortable, most mundane explanation had been systematically and brutally dismantled by cold, hard data. The mystery had not been solved. It had deepened into a chasm. This single, stubborn fact, the push without the gas, became the central paradox of Oumuamua, a cosmic riddle that would force us to question the very nature of what we were seeing. With the comet hypothesis in tatters, the scientific community, driven by its relentless need for answers, began to explore the fringes of celestial mechanics, searching for any other natural phenomenon that could account for the bizarre behavior. Every new idea was a testament to human ingenuity, a desperate attempt to fit this square peg into the round hole of our understanding. One of the first alternatives considered was the gentlest force in the cosmos, sunlight itself. Light, though it has no mass, carries momentum. As photons from the sun strike an object, they impart a tiny, continuous push. This is solar radiation pressure. We see its effects throughout the solar system. It's the force that can subtly alter the orbits of asteroids over millennia, and the reason a comet's dust tail curves away from its gas tail. Could this be the invisible engine pushing Oumuamua? The calculations were straightforward. We know the brightness of our Sunday. We could measure the object's distance and its acceleration. The numbers, however, simply did not work. For an object of Oumuamua's estimated size and mass, assuming it was some kind of rock or icy body with a normal density, the push from sunlight would be 100, even 1,000 times too weak to produce the observed acceleration. It was a fly attempting to push a freight train, but then a fascinating caveat emerged from the equations. Solar radiation pressure times could times be the culprit, but only under one condition. It could work if the object was not a dense cigar-shaped rock at all. It would have to possess an extremely low density and a very large surface area. It would need to be incredibly thin, more like a sheet than a solid body, allowing it to catch the light like a sail catches the wind. The object would have to be, for all intents and purposes, a sail. The implication was so extraordinary that for the moment it was set aside. Science demands that we exhaust all other possibilities first. What if Oumuamua had simply broken apart? Perhaps a small piece had fractured off, and the recoil from that event gave the main body the nudge that we were seeing. This was a plausible, if unlikely, scenario, but again the evidence provided a firm rebuttal. Such a fragmentation event would have dramatically changed the object's rotation, causing its brightness to tumble and flicker in a new chaotic pattern. And we would have likely seen a cloud of debris, the shrapnel from the celestial breakup. Hubble and Spitzer saw none of this. The light curve, the rhythmic flashing of its spin, remained stable. The space around it remained empty. Another explanation withered under the harsh light of observation. The search grew more exotic, still pushing the boundaries of astrophysics. Could Oumuamua be composed of something we had never seen before? Perhaps it wasn't made of water ice or rock, but of something far stranger. A theory was proposed that it might be a solid hydrogen iceberg. Hydrogen, the most abundant element in the universe, freezes only at temperatures just a few degrees above absolute zero. A chunk of it drifting through the interstellar cold could theoretically exist. As it neared our sun, this hydrogen ice would sublimate into invisible gas, providing the necessary thrust without a visible coma. It was a brilliant and creative idea, but it was also, upon closer inspection, deeply problematic. The bonds holding a hydrogen iceberg together would be incredibly weak. The journey through the interstellar medium, a tenuous but vast expanse of gas and dust, would have eroded it like sandblasting. Even the faint starlight in the galactic void would have been enough to sublimate its surface, causing it to evaporate over the millions of years it must have travelled to reach us. Most scientists concluded that a solid hydrogen iceberg simply could not survive the trip. It would have vanished long before it ever found our Sunday. Similar theories involving solid nitrogen or other exotic ices faced the same insurmountable problem of survival. And so a profound and unsettling silence fell over the debate. Every conventional theory, every natural explanation had been rigorously examined and found wanting. The scientific method had led us to a dead end. We were left with a collection of irrefutable facts that refused to assemble themselves into a coherent, naturalistic picture. We had an object that was pushed, but not by outgassing, not by the pressure of sunlight on a normal object, not by fragmentation, not by any known or plausible physical process. This was the scientific void, a vacuum of explanation, and it is in such voids that new ideas, sometimes revolutionary ideas, are born. Into this vacuum stepped Avi Loeb. At the time, Loeb was not a fringe figure. He was the chair of Harvard University's prestigious astronomy department, a prolific theorist with hundreds of publications to his name. He approached the paradox of Oumuamua not as a problem to be solved by forcing old theories to fit, but as a message to be decoded. He looked at the evidence without the bias of expectation, and he dared to ask the one question that had been lingering unspoken in the back of everyone's mind. What if our assumption that it times must times be natural is the one thing holding us back from the truth? His logic was a masterclass in scientific deduction, a process of elimination that led to an astonishing conclusion. He began with the undisputed facts. Fact 1. The object exhibited a strong non-gravitational acceleration. Fact 2. There was a complete and utter absence of any outgassing, no coma, no tail to explain this acceleration. Therefore, the force must be coming from something else. He returned to the idea of solar radiation pressure, the gentle push of sunlight. As we saw, the math only worked if the object was structured in a specific way, if it had a large area and a very low mass. If it was, in essence, a sail designed to catch light, for Loeb this wasn't a flaw in the theory, it was the theory itself. He proposed that we take the data at face value. The object is behaving as if it were a solar sail because that is precisely what it is. He argued that to invent exotic, never-before-seen natural objects like a hydrogen iceberg that couldn't survive the journey was a far greater leap of faith than to consider the possibility that we were looking at a piece of technology, an artifact, a relic from another civilization tumbling through our solar system. The hypothesis was breathtaking, a direct challenge to scientific orthodoxy. He wasn't claiming to have proof of alien life. He was stating with clinical precision that an artificial origin was the most conservative and data-driven explanation left on the table. This object, this light sail or probe, would have spent untold eons drifting through the hostile vacuum between the stars. It would have endured a constant bombardment of cosmic rays, high-energy particles that can shred complex molecules and degrade materials. It would have been pelted by micrometeoroids, tiny grains of sand and dust, travelling at incredible velocities, each impact a microscopic explosion. How could any piece of technology, no matter how advanced, survive such an unrelenting assault for millions, perhaps billions of years? Any conventional spacecraft would have been eroded, shattered, or sterilized into inert dust, unless Loeb speculated it was protected. Unless its hull was not made of passive metal or ceramic, but of something far more resilient. What if its designers had turned to nature's own ultimate solution for durability and self-repair? What if its outer shell was not merely constructed but grown? Perhaps he mused the object was shielded by a layer of organic material, a kind of biological hull, a living or once-living veneer designed to absorb radiation, to seal punctures, to withstand the ravages of deep time. The idea was as radical as it was profound. Our first interstellar visitor might not just be a piece of technology. It might be a fusion of the biological and the mechanical, a vessel wrapped in a skin blurring the very line between life and machine. So where does this leave us adrift in a sea of contradictions? We have an object whose trajectory defies our models, whose composition eludes our spectra, and whose very presence whispers of a journey so vast it strains the human imagination. The dossier of natural explanations, once thick with possibility, now lies thin and tattered, each hypothesis tested and ultimately found wanting. A nitrogen iceberg should have shed its skin in a visible frenzy. A hydrogen shard would have evaporated long before it ever reached our star. A simple cosmic dust bunny, a fractal aggregate of interstellar fluff, would have been torn to shreds by the sun's gravitational embrace. Each theory, stretched to its absolute breaking point, manages to explain one or two of 3I Atlas's eccentricities, but not one of them can account for the entire bewildering suite of behaviors. They fail the test of totality. It is here, in this vacuum of conventional understanding, that the most audacious, the most unsettling, and perhaps the most profound idea begins to take root. An idea that forces us to reevaluate not just the nature of this single visitor, but the very possibility of life in the cosmos. We must ask the question that science, in its cautious conservatism, is often loath to entertain. What if the reason it doesn't behave like a natural object is because it isn't one? This is the precipice where we encounter the work of Avi Loeb and his collaborators, a theoretical framework that abandons the search for a novel, geological or chemical explanation, and instead posits a technological, or more specifically, a times biological times one. The central spine-chilling proposal is that 3I, Atlas, was not a comet or an asteroid but a vessel. And the reason it withstood the ravages of its multi-million-year voyage through the interstellar void is that it was protected by an engineered, self-sustaining and potentially living shield, a biological hull. It is a concept lifted from the pages of science fiction, yet it is being discussed with sober gravity in the halls of astronomical research, because it offers a disturbingly elegant solution to every single one of the object's maddening paradoxes. The idea is not of a metallic ship bristling with antennae, but something far more subtle, more efficient, and perhaps more ancient. Think not of steel, but of shell, not of circuits, but of cells. A structure grown, not built, designed by a form of evolution or engineering so far beyond our own that it appears to us as a force of nature itself. Let's first consider the fundamental problem of any interstellar journey survival. The space between the stars is not empty. It is a shooting gallery, a tempest of lethal energies. For millions of years, any object traversing this expanse is subjected to a relentless fusillade. Galactic cosmic rays, the stripped nuclei of ancient supernovas travelling at nearly the speed of light, punch through matter with atomic-scale violence, shredding complex molecules and sterilizing anything we would recognize as life. The object is also sandblasted by a constant drizzle of micrometeoroids, tiny grains of rock and ice that at cosmic velocities impact with the force of high explosives. Furthermore, it is exposed to the unshielded glare of distant, powerful stars bathing it in hard ultraviolet and X-ray radiation. A common comet, a loose agglomeration of ice and dust, would be degraded, eroded, and fractured by this gauntlet. It would arrive in a new solar system not as a pristine artifact, but as a battered, pockmarked survivor, its surface fundamentally altered. Yet 3I Atlas showed no signs of such a torturous history. It appeared for all intents and purposes intact. This is where the hypothesis of a biological hull presents its first compelling argument. Imagine a structure not inert and brittle like rock, but dynamic and resilient like the chitinous shell of an insect or the bark of a sequoia. A material capable of active self-repair. When a micrometeoroid strikes, the damage isn't a permanent crater, it's a wound. And this hull, using stored energy, or by metabolizing the sparse resources of the interstellar medium, could potentially mend that wound, sealing the breach and restoring its structural integrity. It would be a living armor constantly maintaining itself against the slow, grinding erosion of the void. This inherent toughness, this ability to regenerate, would explain how the object could complete its immense pilgrimage and arrive in our solar system looking so coherent. It didn't just survive its journey, it endured it, its shield holding fast against the abyss. This concept of a living shield immediately confronts the mystery of the missing outgassing. Remember, the key problem with the comet hypothesis was that 3I, Atlas, was accelerating away from the Sun with a gentle, persistent push. Yet our most powerful telescopes could detect no coma, no tail, no vaporous exhaust of sublimating. Ices that should have been driving it. The engine was invisible. A biological hull provides a fascinating, if speculative, answer. What if the acceleration wasn't a crude process of ice boiling off into space, but a far more sophisticated biological or biomechanical function? The surface itself could be the engine. We see analogues on Earth in the process of photosynthesis, where organisms convert light directly into chemical energy. Perhaps this hull was engaged in a form of photonic metabolism, where the immense energy of our Sun was absorbed by its surface and converted directly into thrust, not through a violent expulsion of mass, but through a subtle, controlled process. It could be a change in the hull's reflectivity, creating a pressure differential across its surface. It could be a directed thermal release, venting heat in a specific direction to generate a gentle, continuous push. Or it could be something even more exotic, a biological mechanism that interacts with the particles of the solar wind, the stream of charged plasma flowing from the Sun, using it like a sail on a magnetic sea. In any of these scenarios, the process would be highly efficient, producing the observed acceleration without the messy, visible evidence of a coma. The object would appear quiescent and inert, while its very skin was actively propelling it on its way. The lack of a tail wasn't a contradiction. It was a clue pointing towards a technology so advanced it was mistaken for a ghost. The hull wasn't just a passive shield, it was an active functioning component of a larger machine. Then we have the object's extraordinary shape. Spectroscopic and light curve data suggested a body that was radically elongated, perhaps 10 times longer than it was wide, a cosmic shard tumbling through space. Creating such an extreme shape through natural processes is exceptionally difficult. A spinning body of rock or ice naturally tends towards a more spherical or potato-like shape to minimize rotational stress. An object as elongated as 3I, Atlas, would be under immense strain, constantly threatening to snap in two under its own chaotic rotation. For it to form naturally and then survive the tidal forces of interstellar clouds and stellar encounters for eons is statistically improbable. But if you are not dealing with a pile of rubble held together by weak gravity, but with an engineered structure, the problem vanishes. A biological hull infused with the equivalent of carbon fiber-like biological polymers would possess immense tensile strength, far greater than that of porous, icy rock. It could easily maintain a rigid, elongated form against the centrifugal forces of its spin. The shape would no longer be a product of random chance, but a matter of deliberate design. An elongated form is highly efficient for a number of purposes. It minimizes the cross-section for head-on collisions with interstellar dust. It could maximize the surface area for collecting energy like a leaf turning towards the Sun. Or if it were a probe, it could house long internal components, sensors, or even habitats arranged for optimal function. The bizarre, cigar-like silhouette ceases to be a geological freak of nature and instead becomes a hallmark of sophisticated, purposeful construction, enabled by the structural integrity of its biological casing. This leads us to the tumbling. 3I. Atlas wasn't spinning cleanly around a principal axis like a well-thrown football. It was tumbling chaotically like a discarded bottle drifting on the waves. For a natural body, this is a high-energy, unstable state. The constant flexing from such a motion would over millions of years dissipate energy and likely cause the object to fracture. Again, the biological hull offers a solution. Its inherent strength and potential for self-repair would allow it to withstand these stresses indefinitely. But the hypothesis allows for an even more intriguing possibility. What if the tumbling wasn't a flaw but a feature? In the cold of deep space, this chaotic rotation could be a form of passive thermal regulation. By constantly changing its orientation to distant starlight, No single part of the hull would be perpetually frozen in shadow or perpetually exposed to radiation. It would evenly distribute the minimal energy it received, preventing the formation of thermal stresses that could crack a more brittle, inert object. Upon entering our solar system, this same tumbling motion would serve to evenly distribute the intense heat from our sundae. One side wouldn't be baked while the other flash froze. The entire surface would be warmed in a slow, cyclical rhythm like a rotisserie over a cosmic fire. This could be a crucial function for a biological system, preventing catastrophic temperature gradients and allowing its internal mechanisms or even dormant life to remain in a state of equilibrium. The chaotic dance of 3I, Atlas, which appears so random and uncontrolled to us, might have been the hum of a perfectly designed passive system of self-preservation. It wasn't falling through space. It was performing a carefully choreographed maneuver perfected over an evolutionary timescale we can barely comprehend. Finally, and perhaps most critically for its potential purpose, a biological hull would be a supremely effective radiation shield. If this object were a probe, a seed ship, or any kind of vessel carrying a payload, that payload would need to be protected from the sterilizing bath of galactic cosmic rays. A thin metal hull like one we might build offers minimal protection. High-energy particles would pierce it and create a deadly shower of secondary radiation inside. Rock is better, but heavy and brittle. The ideal radiation shield, as our own physics tells us, is a thick layer of hydrogen-rich material. Hydrogen nuclei, being single protons, are excellent at stopping high-energy particles without shattering into secondary radiation. And what is the basis of all known life? Water and organic molecules both exceptionally rich in hydrogen. A biological hull, several meters thick and composed of complex water-rich organic polymers, would be one of the most perfect radiation shields imaginable. It would be a self-healing, structurally sound, hydrogen-dense blanket, absorbing the lethal energies of the cosmos and protecting whatever lay within its core. It resolves the paradox of how a delicate payload, be it technology or biology, could possibly survive an interstellar crossing. The shield isn't just armor against impacts, it's a bulwark against the invisible death that permeates the void. It is the cosmic chrysalis, a perfect protective layer for a slow, patient metamorphosis across the stars. This single concept, a living, self-repairing, hydrogen-rich structure, simultaneously explains the object's resilience, its inexplicable acceleration, its unlikely shape, its strange tumbling motion, and its ability to protect potential payload. It is the master key that appears to unlock every door at once. For proponents like Loeb, this convergence of evidence is what elevates the hypothesis from mere speculation to a plausible scientific theory. The principle of Occam's razor, which states that the simplest explanation is usually the best, can be applied here in a fascinating way. Is it simpler to believe that 3I, Atlas, was a unique, never-before-seen type of nitrogen iceberg, which also happened to be shaped in a highly improbable way, and which also happened to be tumbling in a chaotic yet stable manner, and which also happened to withstand the interstellar environment perfectly? Or is it simpler to propose a single, alternative explanation that it was an artifact with a biological hull which accounts for all of these disparate facts in one cohesive narrative? The choice, he argues, is between a cascade of compounding natural improbabilities or one singular, profound, and paradigm-shifting reality. We are pushed to the very edge of our scientific understanding, forced to confront a possibility that is as thrilling as it is terrifying. The data from 3I Atlas does not fit neatly into our established categories. It resists our labels. It challenges our assumptions about what is possible in the universe. The biological hull hypothesis, for all its strangeness, provides a framework, a story that honors the data. It paints a picture of a silent, ancient voyager encased in living armor, using the light of stars as both map and engine, tumbling its way through eternity. It suggests that the answer to Fermi's famous paradox, where is everybody, might not be found in radio signals, but in the quiet passage of such artifacts drifting between the stars waiting to be seen. But to accept this, we must cross a monumental threshold. It means accepting that an intelligence, biological or otherwise, not only exists but has mastered technologies that border on magic to our eyes. It means the strange shard that passed through our cosmic backyard was not a rock but a message, a seed, or perhaps just the refuse of a civilization so advanced its cast-offs mimic the wonders of the natural world. This is the weight of the evidence, the core of the debate. Have we in our search for answers simply projected our own fantasies onto an ambiguous set of data? Have we stumbled into the ultimate cosmic mirage? Or are we for the first time looking at the authentic signature of technology from another? Star, a technology cloaked in the elegant and durable architecture of life itself. The silence that followed 3i, Atlas's departure, is now filled with this one resonant question. And as we turn to the intense skepticism and rigorous counter-arguments from the wider scientific community, the search for the truth about our silent visitor only deepens. And so the hypothesis was thrown down like a gauntlet, a biological hull, an organic shield encasing and protecting something within something far more precious than mere rock or ice. It was a breathtaking, terrifying, and profoundly lonely idea. In the hallowed halls of science, such a claim is not met with silence. It is met with a storm, a necessary storm, for science is not a gentle art of consensus. It is a crucible of doubt, a relentless, often brutal process of falsification. Every extraordinary claim must be placed upon the anvil of scrutiny and hammered by the brightest minds until it either shatters into dust or is forged into something resembling truth. The community as one rose to the challenge not out of malice but out of a sacred duty to defend the known laws of the cosmos. The burden of proof, after all, does not lie with the skeptics. It lies with the claim itself. And so began the great intellectual hunt for a ghost, a search for a natural explanation, any natural explanation that could account for the bizarre suite of behaviours we witnessed in our fleeting, mysterious guest. The first and most elegant phantom to be summoned was born from the most common substance in the universe, hydrogen. Imagine theorists proposed that Oumuamua was not a rock at all. Imagine it was a cosmic iceberg, but of a kind we have never seen, composed not of water ice, but of solid frozen molecular hydrogen. A hydrogen iceberg. The idea was on its surface ingenious. It solved one of the most glaring riddles with beautiful simplicity, the complete absence of a visible coma. Hydrogen gas is transparent. If a chunk of frozen hydrogen were to pass by our sun, its surface would rapidly sublimate, boiling off into space and creating a powerful yet utterly invisible jet of propulsion. You would get the rocket effect without the telltale tail. The non-gravitational acceleration would be perfectly explained. This ghostly exhaust would push the object along its path, making it accelerate away from the sun precisely as we observed. The theory painted a stunning picture of a new class of celestial object born in the coldest, densest cores of giant molecular clouds, those stellar nurseries where the universe forges new suns and planets. Perhaps these hydrogen icebergs were cosmic debris, the leftover building blocks of stars wandering the galaxy for eons. For a moment it seemed the puzzle was solved, a new exotic but ultimately times natural times phenomenon. It was a perfect fit for the acceleration and the missing coma. But the anvil of scrutiny has many hammers, and the heaviest is physics. When other scientists began to strike at the hydrogen iceberg hypothesis, it revealed a fatal crystalline fragility. Solid hydrogen is incredibly volatile. It needs to be fantastically cold to exist barely 2 degrees above the absolute zero of empty space. Even the faint ambient starlight that fills the interstellar medium would act like a constant, gentle blowtorch on its surface. Let's trace the journey of this hypothetical object. Forged in the unimaginable cold of a dark nebula, it begins its voyage. For millions, perhaps billions of years, it drifts through the void. Every star it passes, even from light years away, bombards it with photons, warming it, causing its outer layers to peel away. Like a sugar cube in the rain, it would be constantly dissolving its mass, steadily vanishing into the vacuum. Calculations showed that for a hydrogen iceberg of Oumuamua's size to survive such a galactic journey, it would have had to start with an impossibly large initial mass. Worse still was its encounter with our own star. The close pass by the sun would not be a gentle warming, it would be a thermonuclear furnace. The heat would have been so intense that the hydrogen iceberg would have been torn apart, sublimating with explosive violence. It wouldn't have just gently pushed away, it would have disintegrated. It would have vanished in a puff of invisible gas long before it reached the orbit of Mars. The hypothesis, while clever, required an object that could not, according to our understanding of thermodynamics, possibly exist. It solved one mystery only by invoking a physical impossibility. The hydrogen iceberg was a beautiful ghost, but a ghost nonetheless. It could not survive the harsh reality of space. The search for a natural explanation, however, was far from over. If not hydrogen, what about a more robust but still exotic ice? The focus shifted from the interstellar medium to the outer edges of distant solar systems, to the realm of ice dwarfs and frozen worlds. Our own solar system gave us the perfect clue. When the New Horizons probe flew past Pluto, it revealed a stunning world of towering mountains made of water ice floating upon vast, slowly churning glaciers of frozen nitrogen. Nitrogen, the very air we breathe, can become a solid rock-like material in the deep freeze of the outer solar system. And from this observation, a new contender was born, the nitrogen iceberg. The theory was compelling. Imagine a distant star system, one with a super-Pluto or an exo-Pluto in its frigid outer reaches. A massive impact from another body could shatter this world's surface, blasting a fragment of its nitrogen ice crust out into interstellar space. This celestial shard, a piece of a distant alien world, would then begin its long journey towards us. This model held several advantages over the hydrogen hypothesis. Nitrogen ice is far more stable. It is much more resilient to the gentle warmth of starlight, allowing it to survive an interstellar voyage largely intact. Upon reaching our sun, it too would sublimate, creating a rocket effect. While nitrogen gas can sometimes be detected, its signature is faint. It was plausible, scientists argued, that the outgassing could have been just subtle enough to provide the necessary push while evading detection by our telescopes, which weren't specifically looking for it. The shape too could be explained. As the shard travelled, the constant slow sublimation would erode it, sculpting it into a flattened, pancake-like or cigar-like shape, preferentially wearing away its thickness rather than its length. This erosion model seemed to neatly account for the extreme dimensions inferred from Oumuamua's changing brightness. Here was a complete narrative, a chain of events from birth to observation, grounded in the physics we see in our own cosmic neighbourhood. It was plausible, it was testable, and it was beautifully natural. For many in the astronomical community, this became the leading theory. It was the safe harbour in a sea of radical speculation, but even this harbour was not entirely safe from the tides of probability. When mathematicians and planetary scientists began to run the numbers, the nitrogen iceberg hypothesis started to reveal its own extraordinary requirements, its own form of unobtainium. First, there was the sheer quantity of material required. To create one Oumuamua, you don't just need one exo-Pluto. You need a vast population of them throughout the galaxy. Then you need a vast number of impact events energetic enough to not only chip off a fragment, but to eject it from its star system's gravitational grip, a feat requiring colossal energy. And then, of all the billions of shards potentially launched, one of them has to be sent on the precise pinpoint trajectory to cross the infinitesimally small volume of space occupied by our solar system at the exact time we were looking. The calculations were stark. The mass of exo-Pluto crusts that would need to be ejected into the galaxy to make the detection of one object like Oumuamua statistically likely was astronomical. It would require every star in the Milky Way to have shed on average more than the entire mass of the Earth in nitrogen fragments. The galaxy would have to be absolutely littered with these objects, a celestial minefield of frozen nitrogen. We should be seeing them constantly. Yet in all our years of looking, we have seen only one Oumuamua. The nitrogen iceberg theory didn't invoke a physical impossibility, but it did invoke a statistical miracle. It asked us to believe in a galactic architecture so vastly different, so much more prolific in producing these specific objects than our current models suggest, that it bordered on wishful thinking. To explain one anomaly, it required us to postulate an entire unseen infrastructure throughout the cosmos. The theory was physically possible, but was it probable? Or was it just another ghost dressed in more plausible clothes? The debate raged, but a definitive answer remained elusive. The ghost of Oumuamua refused to be so easily exorcised. With the comet-like explanations struggling under the weight of their own requirements, a third, perhaps even more radical natural idea emerged from the fringes of theoretical astrophysics. What if Oumuamua wasn't solid at all? What if it wasn't a shard or a rock or an iceberg? What if it was almost nothing? The idea was that Oumuamua could be a cosmic dust bunny, an extremely low-density, highly porous aggregate of ice and dust grains held together by little more than electrostatic forces. Think not of a rock, but of a celestial snowflake or a fractal, a vast, fluffy structure that was mostly empty space. This wasn't just a wild guess. It was rooted in our understanding of how the first planetary building blocks, or planetesimals, form. Tiny dust grains in a protoplanetary disk clumped together, forming larger and larger fluffy fractal-like structures. Perhaps Oumuamua was one such primordial object that was ejected from its nascent solar system before it could ever solidify into a proper asteroid or comet. This fluffy aggregate model had one spectacular advantage. It provided a way to explain the acceleration without any outgassing at all. An object with an enormous surface area but incredibly low mass would be exceptionally susceptible to the gentle, persistent pressure of sunlight itself. Solar radiation pressure, the constant stream of photons flowing from the sun, acts like a wind pushing on everything it touches. For a dense, massive object like an asteroid, this push is negligible, easily overcome by the sun's gravity. But for a vast, lightweight object, a cosmic sail made of dust, this pressure could be significant. It could be the very force that was pushing Oumuamua, the mysterious engine behind its non-gravitational acceleration. No invisible gas was needed, no cometary tail, just the pure, clean pressure of light. It was an exquisitely simple and elegant solution, a fragile ghost pushed by a phantom wind. But like every theory before it, the cosmic dust bunny had to face the brutal realities of an interstellar journey. Its greatest strength, its ethereal fragility, was also its most profound weakness. How could such a delicate structure possibly hold itself together? The tidal forces during its slingshot around our sun would have been immense. Gravity would have pulled more strongly on the side of the object closer to the sun than on the far side, creating a stretching, shearing force that should have ripped such a loosely bound collection of dust to pieces. Furthermore, the object had to be spinning, tumbling end over end every 7 to 8 hours. This rotation would create its own centrifugal forces, trying to fling the object apart from the inside out. Calculations suggested that for a dust bunny of this size to survive both the sun's tidal forces and its own rotation, it would need some internal tensile strength, some kind of cosmic glue holding it together. But the very premise of the model was that it was held together by nothing more than feeble electrostatic attraction. It was a paradox. To explain its acceleration, it had to be fantastically light and fluffy. To explain its survival, it had to be surprisingly strong and resilient. It could not be both. The cosmic dust bunny, like the hydrogen iceberg, seemed to be an object that would have destroyed itself in the very act of being observed. It was another beautiful idea, another clever ghost, that seemed to dissolve upon closer inspection. And this is where we found ourselves, in a state of profound and unsettling intellectual stalemate. Each natural explanation, born from brilliant minds, working at the peak of their creativity, ultimately failed to account for the complete picture. They were not wrong in the conventional sense, they were incomplete. Each one was like a key that fit one lock on a door covered in them but could not turn the others. The hydrogen iceberg unlocked the invisible coma but was shattered by the lock of thermal physics. The nitrogen iceberg unlocked a plausible origin story but was blocked by the immense lock of statistical improbability. The cosmic dust bunny unlocked the acceleration with elegant simplicity but disintegrated against the lock of structural integrity. The rigor of the scientific method in its determined effort to find a conventional answer had performed an extraordinary, if unintentional, service. It had systematically dismantled all the most plausible natural explanations one by one, exposing their hidden flaws and unobtainium requirements. The skeptics, in their attempt to slay the dragon of speculation, had instead given it scales of hardened steel. They had proven more effectively than any proponent could just how stubbornly unique, how infuriatingly anomalous Oumuamua truly was. The silence that followed this exhaustive process was not one of agreement. It was the silence of a mystery that had deepened, of a puzzle that had become more complex with every failed solution. The process had not eliminated the extraordinary hypothesis. Quite the opposite. By failing to find a viable natural alternative that fit all the data, it left the most uncomfortable, the most paradigm-shifting possibility still standing. Not proven, not by a long shot, but it remained stubbornly, unnervingly in contention. The question mark at the end of the universe had grown larger, bolder, and now, with the arrival of 3I, Atlas, an object displaying even more bizarre and seemingly deliberate characteristics, that lingering question was about to transform into a chilling declaration. And so the battle lines were drawn, not on some distant field, but in the hushed halls of academia, in the peer-reviewed pages of scientific journals, and across the flickering screens of global conferences. The mystery of Oumuamua and the subsequent questions raised by the perplexing nature of 3I, Atlas, had not unified the scientific community in a shared quest. Instead, it had cleaved it in two, triggering a kind of intellectual civil war. On one side stood the defenders of established naturalistic explanations, armed with Occam's razor and the formidable power of probability. They saw anomalies, yes, but anomalies that could, with enough ingenuity, be forced to fit within the known laws of physics and chemistry. They proposed cosmic icebergs of pure hydrogen so porous they were almost nothing, yet solid enough to survive an interstellar journey. They conceived of nitrogen shards blasted from the surfaces of Pluto-like dwarf planets in some distant, unknown star system. They even modelled celestial dust bunnies, fractal aggregations of matter so light they could be pushed by the gentle pressure of starlight. Each hypothesis was a masterpiece of theoretical physics, a testament to the human mind's ability to conjure explanations for the seemingly inexplicable. Each was an attempt to cage the wild beast of the unknown. Yet for every elegant solution proposed, a host of inconvenient new problems arose. A hydrogen iceberg, while explaining the acceleration, would have evaporated far too quickly in the interstellar medium, sizzling away like a snowflake on a hot plate long before it ever reached our sundae. A nitrogen shard, a more robust candidate, required a very specific and violent origin story, a cosmic coincidence of such precision that it stretched the bounds of credulity for many. These natural explanations, intended to be the simpler answer, began to feel baroque, convoluted, and in their own way incredibly exotic. They demanded we believe in objects no one had ever seen or even theorized before. Oumuamua's arrival. On the other side of this intellectual chasm were those who dared to whisper the alternative. They looked at the same data, the extreme shape, the trajectory nudged by an invisible hand, the complete and utter lack of a cometary tail, and saw not a natural freak but an artificial artifact. And with 3I Atlas, they saw a pattern emerging, a second data point suggesting that such objects might not be unique. This was not a position taken lightly. It meant standing against centuries of scientific caution, inviting ridicule, and risking professional reputation. The biological hull hypothesis in particular became the conflict's most charged battleground. It was for many a line too far. Proposing an inert piece of technology, a solar sail or a defunct probe, was one thing, but suggesting that the object itself could be a form of casing, a protective shell for interstellar life, plunged the debate into the realm of science fiction. The evidence, after all, was entirely circumstantial, an argument built from the absence of conventional explanations rather than the presence of definitive proof. There was no radio signal. There was no direct observation of a technological signature. There was only the object's deeply strange behavior. The conflict settled into a grinding stalemate. The naturalists could not definitively prove their case, as each of their models had significant, perhaps fatal flaws. The proponents of an artificial or biological origin, meanwhile, were armed with a hypothesis that, while explaining the observed phenomena with remarkable elegance, lacked the single, unambiguous piece of evidence needed to overturn the scientific consensus. They had a motive and a suspect, but no smoking gun. We were left staring into the abyss with two sets of impossibilities. Was it an object of a type we have never seen created by a process we do not understand? Or was it a thing made by beings we have never met, sent from a place we cannot imagine? This is where the story could have ended. A frustrating, unresolved cosmic puzzle. A file stamped unexplained and left to gather dust in the archives of astronomy. But that is not what happened. Because the true legacy of Oumuamua is not the answer it failed to provide, but the profound and permanent questions it forced us to ask. Its fleeting visit was a shock to the system, a jolt of adrenaline to a field that had perhaps grown too comfortable in its assumptions about the sky. For over a century, our search for extraterrestrial intelligence had been almost entirely passive. We built colossal electronic ears like the Arecibo Observatory or the Allen Telescope Array, and we listened. We waited for a signal, a cosmic hello sent across the void, assuming any intelligence out there would use the same methods of communication we did. We were waiting for a message in a bottle. Oumuamua suggested that the messages might not be broadcasts at all. They might be the bottles themselves. It fundamentally reshaped our understanding of what an alien artifact could be. It might not be a shining active probe, blinking with lights and beaming radio waves. It could be dark, silent, dead, a piece of cosmic driftwood, a derelict or perhaps even a seed tumbling through the darkness for millions or billions of years. The scientific community, galvanized by the frustration of having let our first confirmed interstellar visitor slip through our fingers, underwent a seismic shift in perspective. The feeling was universal: never again. Never again would we be so unprepared. The first and most immediate change was in how we watched the heavens. The Vera C. Rubin Observatory in Chile, a monumental achievement in observational astronomy, was already under construction when Oumuamua flew by. But the incident infused its mission with a new and urgent purpose. This next-generation telescope is designed to survey the entire visible sky every few nights, creating a motion picture of the cosmos of unprecedented detail. Its primary goal is to map the universe, but a critical secondary function is now to serve as our planet's first dedicated interstellar tripwire. Scientists began developing sophisticated new algorithms, AI-driven sentinels, specifically designed to sift through the torrent of data the Rubin Observatory would produce. These programs are not just looking for points of light, they are looking for strangeness. They are trained to flag any object with a hyperbolic trajectory, the telltale signature of an interstellar origin. They are programmed to search for the bizarre, to identify the outliers that don't conform to the behavior of the asteroids and comets born in our own solar system. We have built a finer net, and we are now actively trawling the cosmic ocean for visitors, rather than simply waiting for them to wash ashore. This proactive stance extended beyond mere detection. The debate around Oumuamua's composition, particularly the more radical ideas, forced us to reconsider what we are even looking for. Before the search for life was the search for biology as we know it, for water, for organic molecules, for atmospheric biosignatures on distant exoplanets. The biological hull hypothesis, controversial as it was, acted as a powerful intellectual catalyst. It compelled us to think about life not just as a planetary phenomenon, but as a potentially interstellar one. It made us consider the possibility of necrosignatures, the signs of life that is no longer living. What would a billion-year-old shell, designed to protect its precious cargo from the ravages of radiation and the cold of deep space, look like? What materials would it be made from? Could its very structure, its resistance to degradation, be a signature in itself? Laboratories around the world began new lines of inquiry, exploring how complex organic materials or theoretical biopolymers might behave after eons of exposure to cosmic rays. The conversation expanded from "is there life out there?" to "what are all the forms, living and dead, that life's footprint could take across the galaxy?" It was a paradigm shift born from a single enigmatic data point. Out of this ferment of new ideas and newfound urgency, one project emerged that perfectly encapsulates this transformation from passive listening to active pursuit. It is a mission concept of breathtaking audacity, a plan that would have been confined to the pages of science fiction just a decade ago. It is called Project Lyra. The goal of Project Lyra is not to wait for the next Oumuamua to visit us. The goal is to go to it. It is an acknowledgement that to truly understand these objects, To finally resolve the debate between natural phenomena and artificial craft, we must get up close. We must touch them. The challenges are almost beyond comprehension. An interstellar object moves at speeds that mock our fastest spacecraft. Oumuamua, for instance, was travelling at over 196,000 miles per hour relative to the Sun as it departed our system. To catch it, or one like it, would require a complete revolution in propulsion technology. A conventional chemical rocket like the mighty Saturn V that took us to the Moon would be like trying to catch a bullet with a horse and buggy. It would never get there in time. The scientists and engineers behind Project Lyra are therefore looking to the very edges of our technological capability. One leading concept involves what is known as a nuclear thermal or nuclear electric propulsion system. This would use the immense heat from a small onboard nuclear reactor to superheat a propellant like hydrogen, creating a far more powerful and efficient thrust than any chemical engine could ever hope to achieve. Another, even more advanced proposal involves a solar thermal slingshot. The spacecraft would first dive perilously close to the Sun, perhaps even closer than the Parker Solar Probe has dared to venture. During this fiery passage, it would deploy a massive heat shield to absorb the Sun's ferocious energy, using it to heat a propellant. Then, firing its engine at the moment of closest approach, it would combine the engine's thrust with the Sun's immense gravity in a maneuver called the Oberth effect. This gravitational assist on steroids would fling the spacecraft out of the solar system at astonishing speeds, potentially fast enough to chase down a departing interstellar guest. The engineering required is staggering. The probe would need to withstand temperatures that can vaporize tungsten. It would need to navigate with pinpoint precision. It would have to operate autonomously for decades, perhaps even centuries, as it crossed the unimaginable gulf between the stars. And it must be ready. The entire mission concept is predicated on speed. The moment the Rubin Observatory or another survey detects a promising candidate, the clock starts ticking. A launch window might be open for only a few months, or even just a few weeks. A pre-built interceptor would need to be on standby, fueled and ready on the launch pad, waiting for a target that might not appear for another year or another decade. It is perhaps the most ambitious scientific gamble in human history. Project Lyra is more than just an engineering blueprint. It is the physical manifestation of our cosmic curiosity. It is humanity's statement of intent. We will no longer be passive observers of the universe. We will be active explorers. We will knock on the doors of our celestial visitors. Imagine the moment. After a journey of decades, our robotic emissary finally closes the distance. The first grainy images appear on screens back at mission control. The long, dark shape of the visitor resolves out of the blackness. Is it a jagged, tumbling shard of alien ice, pitted and scarred by its long journey? Or do we see the glint of manufactured metal, the clean lines of a constructed object? Do we see panels, antennae, or something far stranger, a surface that is not geological but structured, patterned, perhaps even biological in its ancient frozen texture? For the first time we would have an answer. The debate that has raged since 2017 would finally be settled. The cost would be enormous, the technological hurdles immense, but the potential reward is the greatest prize imaginable, the answer to the question of whether we are alone. Yet, as we design these incredible missions and build these new celestial dragnets, the ghost of the original mystery remains. For all our ambition, for all our new technology, the truth about Oumuamua itself is now forever beyond our grasp. It is receding from us at an incredible speed, having already passed the orbit of Neptune, a faint and undetectable speck in the overwhelming darkness. It is heading in the direction of the constellation Pegasus, a silent messenger returning to the void from which it came. It will not return in our lifetimes, or in the lifetime of our species, or likely even in the lifetime of our planet. Its secrets are its own once more. We had our chance. We had a few precious weeks where this enigmatic traveller graced our skies, and we were only able to see it as a faint, unresolved point of light. We threw our best telescopes at it, we analysed its trajectory with unprecedented precision, and still it left us with more questions than answers. It was a cosmic test, and it revealed the limits of our knowledge, the boundaries of our imagination. The lack of consensus isn't a failure of the scientific method. It is a reflection of the sheer, unadulterated strangeness of what we saw. Oumuamua and its perplexing sibling, 3i, Atlas, have become modern myths, celestial legends, whose ultimate truth remains tantalizingly, maddeningly out of reach. They are the ones that got away, and so we arrive at the quiet shore after a tempestuous voyage across the unknown. We have tracked a phantom through the solar system, chasing its faint signature from the moment of its discovery to its final fading departure into the void. We have dissected its motion, debated its composition, and dared to imagine its origin, journeying from the comfort of known physics into the unsettling realm of radical possibility. What began as another curious point of light, a fleeting visitor from beyond, has become something far more resonant, something that resists easy categorization. It has become a mirror reflecting not only the distant starlight it traverses, but also the deepest questions we have ever thought to ask. The journey to understand this enigmatic object and its predecessor, Oumuamua, has not truly been about them. It has been about us. It has been a profound exploration of the limits of our knowledge, the biases of our perception, and the sheer unyielding courage it takes to confront a mystery that might just rewrite everything we thought we knew about our place in the universe. In the end, this interstellar traveler became the ultimate cosmic Rorschach test, where one seasoned astronomer saw the sublime, chaotic beauty of nature, a cosmic shard carved from a nitrogen glacier on some distant frozen world. Another saw the unmistakable hallmark of intention. The very same data, the same photons collected by our most advanced instruments, painted two irreconcilable portraits. One was a picture of magnificent but ultimately familiar natural processes, a testament to the universe's endless capacity for creating exotic yet understandable phenomena. The other was a far more disquieting image, one that hinted at a technology so advanced it borders on the magical, a structure built not of rock and ice, but of something more complex, something that could even be biological. This fundamental divergence in interpretation reveals less about the object itself and more about the very nature of scientific inquiry. Science is not a monolithic entity that delivers absolute truths. It is a human process, a conversation, often a heated argument carried on across generations. You see, for every argument that pointed toward a natural explanation, there was a persistent nagging anomaly that defied it. The proposed nitrogen iceberg, a brilliant and creative solution, struggled to account for the object's apparent structural integrity, its ability to survive the brutal journey through interstellar space, and the fiery passage past our Sunday. The hydrogen iceberg hypothesis, while elegantly explaining the non-gravitational acceleration, required a formation environment that we have yet to observe anywhere in the cosmos. Every naturalistic model we constructed, no matter how ingenious, seemed to demand a unique one in a trillion set of circumstances. It required us to accept that we had just witnessed the astronomical equivalent of a perfect storm, a celestial coincidence of mind-boggling improbability. And it is here at the razor's edge of probability that the alternative hypothesis, however extraordinary, begins to exert its gravitational pull on our curiosity. The opposing view, the one that speaks of an artifact of a biological hull, is not born of a rejection of science, but from a deeper allegiance to one of its core principles: to follow the evidence wherever it leads, no matter how uncomfortable the destination. It asks us to consider that perhaps the object's strangeness is not a coincidence, but its defining feature. Perhaps its thinness, its trajectory, its anomalous acceleration are not a collection of independent puzzles to be solved, but are instead the correlated signatures of its function. This perspective forces us to confront a humbling possibility that we are not witnessing a freak of nature, but a piece of technology so far beyond our own that we can barely recognize it as such. We are like ants crawling across a smartphone, aware that it is not a rock, but utterly incapable of comprehending the global information network it represents. We can measure its properties, its hardness, its warmth, but we lack the context to understand its purpose. This schism in the scientific community is not a failure. It is a sign of robust health. It is the friction of brilliant minds grinding against an unyielding problem, and in that friction sparks of new understanding are generated. The debate over these interstellar objects has forced us to re-examine the very foundations of our assumptions. What does a piece of extraterrestrial technology look like? For decades, our search for extraterrestrial intelligence, SETI, was dominated by the metaphor of the radio. We listened for signals, for engineered patterns of electromagnetic radiation, assuming any advanced civilization would communicate in a way we could easily recognize. We were waiting for a deliberate phone call, but Oumuamua and its perplexing successor have suggested a radically different possibility. They have introduced us to the concept of cosmic archaeology. What if the evidence is not a message but a relic? A silent, discarded piece of hardware drifting through the galaxy like a potsherd in a river, carrying with it the story of its makers. This single idea has irrevocably transformed the landscape of the search. It has broadened our perspective from merely listening for whispers to actively scanning for physical artifacts. It has legitimized the search for what some are now calling lurkers, unseen, perhaps ancient probes in our own solar system. New projects fueled by this newfound paradigm are already underway. The Vera C. Rubin Observatory, with its unprecedented ability to scan the entire visible sky every few nights, will undoubtedly discover dozens, if not hundreds, of new interstellar visitors. We are building a finer net, preparing for the next object that comes our way, ensuring that this time we will be ready. We will have more than just a few fleeting days of observation. We will have a coordinated global response ready to characterize it in exquisite detail, perhaps even to send a mission to intercept it. The intellectual courage displayed by those willing to publicly entertain the extraterrestrial hypothesis cannot be overstated. In a field where credibility is paramount and speculation is often punished, they chose to embrace the anomaly. They chose to ask the daring question, what if this act has had a liberating effect on the next generation of astronomers and astrobiologists? It has given them permission to think outside the established corridors of thought, to pursue high-risk, high-reward research without fear of ridicule. The conversation has been cracked wide open. Suddenly, discussions about biosignatures, technosignatures, and the engineering principles of light sails are not confined to the fringes. They are entering the mainstream of astronomical discourse. We are being forced to consider that the universe may not only be stranger than we imagine, but stranger than we can imagine. This entire saga forces us to zoom out, to look back upon our own tiny, fragile world from the cold interstellar gulfs through which these objects travel. For all of human history, we have looked up at the stars and felt a profound sense of isolation. We have built our philosophies, our religions, and our civilizations around the central, unspoken assumption that we are alone. We have defined ourselves by our uniqueness. The mere possibility that these objects could be artifacts of another intelligence challenges that foundational belief. It suggests that the void is not empty. It hints that mind and intention may not be a fleeting accidental property of this one small planet, but could be a fundamental recurring feature of the cosmos. Think of what that truly means. It means that somewhere out there, perhaps orbiting a star so distant we cannot even resolve it, another form of life once looked up at its own sky and had the same thoughts we do. It means they felt the same pull of curiosity, the same drive to explore, the same desire to transcend their own celestial cradle. It means they succeeded. They built something, perhaps something like the very object that just tumbled past us, and they sent it out into the great darkness. Whether as a probe, a derelict ship, a piece of art, or a tomb, its existence would be a testament to the fact that intelligence is not a dead end. Life can and does find a way to reach for the stars. And if they could do it, then what does that say about our own future? Suddenly, the dreams of interstellar travel, of becoming a multiplanetary species, seem less like science fiction and more like a developmental stage we have yet to cross. Reach. These visitors, whatever their ultimate nature, serve as a cosmic wake-up call. They remind us of the sheer scale of our ignorance. We have explored our own planet, mapped our solar system, and peered back to the dawn of time, yet we can be completely blindsided by a small, silent object passing through our own cosmic neighborhood. It is a humbling lesson in cosmic modesty. It tells us that we have not figured it all out, that our best theories are still incomplete, and that a universe of wonders and surprises still awaits us. The mystery is the point. The uncertainty is what drives us forward. It is the engine of science and the fuel for our imagination. Not knowing is a gift because it gives us a reason to keep looking, to keep building, to keep striving. So the vigil continues. Our telescopes, our digital eyes, remain fixed on the heavens, more alert now than ever before. We scan the darkness not just for the familiar glow of comets and asteroids born of our own sun, but for the interlopers, the messengers from other realms. We are no longer just astronomers. We are sentinels watching the shore of an infinite cosmic ocean, waiting for the next bottle to wash ashore. The data from 3i, Atlas, will be analysed for decades to come, its secrets slowly teased out by more powerful algorithms and more creative minds. But its true legacy is already written. It has prepared us, it has sharpened our tools, and more importantly, it has sharpened our minds. It has taught us that we must be prepared for the unexpected, for the thing that does not fit, for the visitor that challenges our every conception of what is possible. We stand on the precipice of what could be the single greatest discovery in human history. The answer to the age-old question, are we alone, may not come in the form of a booming radio signal or a grand celestial armada. It might come as another faint, fleeting blip of light, another anomalous trajectory, another silent ghost gliding through the darkness between the stars. And when it comes, we will be there to see it. We will be ready to ask the right questions, armed with the hard-won wisdom that the universe rarely conforms to our expectations. We will search, we will wonder, and we will wait forever vigilant for the next interstellar traveler, hoping that it might finally definitively tell us its story. A story that in the end will also be our own.